All right, so this is section 1.2, Epsilon-Delta definition of a limit. This is what chapter 1 all comes down to, guys. This is the precise definition of the limit that we're going to be building up to. So first, we're going to kind of do an introduction, try to, put our toes in the water before we jump into the deep end. All right, so given a function y equals f of x, okay, and an x value equal to c, we say that the limit of a function f as x approaches c is the value L. Okay, so what does that mean? Y approaches L whenever x approaches c. Okay, so that's one way of interpreting it. Another way of saying it is that y is near L whenever x is near c. That's one way to think about a limit in its most basic idea. However, the problem with this is that the definition is not exact. In mathematics, we need to be very precise in our language, one of the key components of calculus. And so near is not good enough for us. We need to have a mathematical definition of what near, x near to c represents, okay? So here's a better definition. If x is within a certain tolerance level of c, meaning so we're within some interval close to c, then the corresponding value, okay, the corresponding value y, so I input x, it outputs y, just like a typical function, right, is within some certain tolerance of L, okay? Now, what are these tolerances known as? They are delta and epsilon tolerances. So the delta tolerance is the x tolerance, and the epsilon tolerance is the y tolerance, okay? So let me show you in a picture what I'm talking about here, because this is very abstract, right? So say we've got this square root function here, okay? And now I'm going to have an input c, okay? So I've got my c here, I input it there, and then an output L, okay? So what am I saying here? Y is near L, so the y value is near L when the x value is near c. Does that make sense? So the y is near L when the x value is near c. So first, when we're doing these proofs here, we choose an epsilon, a y tolerance first. That's the first thing we have to do. We have to say, how much of an error are we willing to accept that we can be off by? Okay? So maybe your error, maybe you know the exact value is L equal to 5. That's the exact answer. But we're willing to say we'll be within 0.01 on both sides. So my answer that I get when I estimate could be like 4.99 to 5.01, right? So an error, a tolerance of plus or minus 0.01, any answer in this range would be close enough. Okay, so depending on how small you make your tolerance, the more accurate your answer has to be, and the more narrow that band becomes. So first thing you do is you choose your epsilon. So right now we're just making everything arbitrary. So I have some epsilon, so I go a distance epsilon downward, okay? And so once I choose my epsilon, then I have my bound that goes over to it. And then what? I can bring that down here. And that tells me my x value that corresponds with that chosen epsilon. And we're going to call that tolerance, we're going to call it our delta tolerance. The x tolerance is delta. And I'm going to call this D1 because this is on the lower side. We're going to have another one on the upper side, okay? So that's D1. All right, that's that lower one. And then instead of going minus epsilon, now we're going to add epsilon to get this limit plus epsilon value up here. So the epsilon tolerance, the y tolerance here, remember this is your y value, these are your x values, right? Okay, and so we follow where it hits the curve and we come down, and this is the input that it takes to get back over to here, okay? And we're going to call that distance delta 2. So we have a delta 1 and a delta 2, okay? And this is based off of the epsilon that was chosen first, okay? So the epsilon that was chosen first determines what the delta 1 and delta 2 are. Notice that this is the same distance as this is right here. However, this distance here, that is very different than that distance there. So D1 and D2 don't equal each other, even though this upper tolerance and that lower tolerance are equal, okay? The only way they might be equal is if you're dealing with like a straight line, okay? Slope 1 or something. All right. Now, I'm going to shade that area in there, and that represents that bandwidth. So any values in here fall in this little bandwidth in here, clearly, okay? So that is my delta 1, okay, width right there. And then over here, any values that fall into this range y value in there will be mapped from this domain, this input over here. So any values that I plug in here get mapped. So all of this stuff right here gets mapped into this little bandwidth right here from that curve, okay? Now, what do you notice here? This delta 1 bandwidth right here, we have the same delta 1 bandwidth over here. And the delta 1 is clearly shorter than the delta 2. So what are we going to do to ensure that our bandwidth down here is within the input of the outputs up here? Well, what I'm going to do is I'm going to pick the smallest of D1 and D2, and I'm going to call that delta, okay? Because now if I designate this to be delta, okay, then this bandwidth right here, all right, so that all gets mapped nicely into this area here. The problem would be if I chose this to be delta, that would mean I would have to go out this way over here. Well, guess what would all of a sudden happen? Now everything in here would be considered, but guess what? We've got a problem because this is not it within the bandwidth. So that's why we pick the smaller of the two D1 and D2 so that we can ensure that we are within our green shaded region here when we do our output from the given inputs. Okay? So if X is within delta units of C, okay, so what does it mean to be X to be within delta units of C? So remember we said our D1 was our delta, right? So the X value is within D1 units of C. So what does that really mean? That means we're starting at C and we go out D1 this way and we go out D1 this way. So if our X values are from here to here, then the corresponding Y value is within epsilon units of L. And so if I follow this up here, I can clearly see that all of these Y values are in here are definitely within the band of epsilon from L, okay? So that's what that statement is saying there. So very complicated, little statement going on here, but that's what's going on. If x is within delta units of c, then the corresponding value of y is within epsilon units of L. Okay? All right, so let's focus more mathematically on what it means to have x within delta units of c. Okay? So mathematically, all right, mathematically, that means that x minus c, x minus c in absolute value is less than delta. Okay? So what does that tell me? That tells me that mathematically, if I do my absolute values, okay, I can rewrite this as x minus c is less than delta, but greater than negative delta. That's the definition when I do absolute value less than some number, okay? Remember, think of absolute value as the distance, okay? So the distance between x and c is delta or less, okay? So what does that mean? That means the distance for any random x that I choose is any x value in this range here, delta or less. Now, if I solve for x, where is that going to put me? I add c to all three places. And what does that do? That gets me delta plus c and c minus delta. Okay? So we have x value dependent on the c minus delta and the c plus delta. Okay? The y is within epsilon units of L. Mathematically, what this is saying is that I have the distance between the y value and the limit is less than the tolerance, the y tolerance, epsilon, okay? And so if this is the case, mathematically, y minus L is less than epsilon, but greater than negative epsilon. So if I add L to both sides, or add L to all three pieces, right? I have L minus epsilon on the lower side and L plus epsilon on the higher side. So this is where the L minus epsilon comes into play and the L plus epsilon comes into play here. Okay? So this C minus delta is right here, and the C plus delta is right here. Okay? Now, since epsilon and delta are tolerances, they can be any positive value, but typically epsilon and delta are really small values, okay? Arbitrarily small. Typically I say epsilon, let epsilon be greater than 0, okay? So it's not equal to 0, meaning that there is some error, but it's so arbitrarily small that you might as well not have any error at all. You can get as close as you feel comfortable, okay? And so that's going to be the key in helping us prove these limits. So these are typically, epsilons are very small numbers, okay? Now, here is the formal definition right here. This is the definition. The limit of a function f, let I be an open interval containing c, and let f be a function defined on I except possibly at c. Okay, so this is that key that I kept pointing out in the videos, but we really didn't go into the example too much. You've got this open interval, okay? So some I open interval, right? And the open interval contains this value c. And so the function is defined on this open interval. But there's this possibility that there's this hole at c, okay? So maybe it's not defined at c itself. That's what allows us to do those canceling of factors when we're taking that limit as x approaches c. So that's the key there when you're talking about the limit as x goes to c, right? It's all the values in a neighborhood around c, but there's the possible exception that we can exclude c itself. Now, sometimes it is the case that c is actually defined there, but it does not have to be defined there, okay? So the limit of f of x as x approaches c is denoted here. This is the formal definition. What this means is that for given any epsilon greater than 0, there exists a delta greater than 0, definition guys, such that for all x values in the interval, remember we had our interval here, okay, with the possible exception of x equal to c itself, okay, that's where x equals c itself, if x, the distance between x and c is less than delta, then the distance between the function value and the limit is less than epsilon. Okay, so that's expressed in this picture here. If we are within this bandwidth here, then the output will be within this bandwidth here. That's the guarantee. Okay, that's the idea of the limit there. All right, so mathematically, just for funsies, I'll show you the mathematical notation here. So the limit as x approaches c of f of x is equal to L. This little symbol stands for all epsilon greater than 0, there exists a delta greater than 0, such that the distance between the x value and c is less than delta, but also greater than 0. What does that mean, to be greater than 0? That means that we're eliminating the possibility that there's 0 distance between x and c. So we're eliminating the possibility of actually choosing an x equal to c. So it's all the x's in this band here except for c. Okay, that's what that's telling me there. Okay, those are all the possible x values right there. Then what does that imply? That implies that f of x, the absolute value of f of x minus L, is less than the tolerance, the y tolerance that we set. Okay? So very powerful definition there. All right? And so I just wanted to introduce that definition to you. You might have to watch this video 2 or 3 times. Okay? And you may never get it. Okay? But this is a very deep concept here, and that's kind of why I waited till the end of the chapter to introduce this, because I wanted you to get really familiar with limits before I give you the formal definition. But this definition, you'll focus a whole lot more on this definition when you get into analysis. But really the idea is that if I can set my x to be within delta of this c value, okay, then that will necessarily require that the output be within epsilon of the L value, of the L output, okay? And if we make epsilon arbitrarily small, then I can get as close to this number as I so desire, which that's what allows us to get as accurate as we want to, even if we can never find the exact answer. This is what helped people, in NASA and whoever they were developing functions to calculate complex problems that didn't have exact solutions. This calculus here that allowed us to get as near to y as we needed to be successful to get the exact measurements for the projectiles. This is what allowed us to get to the moon, okay? So you think about it, you have some x input of 1.0032, some crazy digits, okay? You might have to go out 25 digits just to get to that exact amount that you need so that you don't overshoot the moon. Because when you're talking about traveling from the Earth to the moon, that is a huge distance. And if you're just off by, maybe a tenth of a degree, okay, that could be enough to make you miss the moon by 3 miles. All right, so it was very important for them to be able to get as close to the approximate solution as possible as deemed necessary. And that's the idea of choosing your set tolerance level. So calculus could not have gotten to the moon without calculus. All right, guys.